Here we have one of my favorite subjects, electrical circuits. So let's begin. In the circuit shown above, the switch S is initially in the open position, which means it is neither connected to the terminal A nor to B. Then the switch is moved to position A. Part A asks us, determine the current through the 20 ohm resistor immediately after the switch is moved to position A. So when the switch is moved to position A, we are going to draw the equivalent circuit. The circuit is going to look like this. It's a 30-volt battery connected to a 10 ohm resistor. Here we have on the other end a 20 ohm resistor. This is a 30-volt battery. Now, this is connected to a 50 microfarad capacitor. Initially, when S was disconnected, the capacitor is obviously discharged or uncharged. And as we connect it, the capacitor slowly charges over a long period of time, and thus it doesn't block the flow of current and instead acts as a closed circuit or a closed switch. So the equivalent circuit is as such. Here we have two resistors in series, making their equivalent combined resistance in series to be R1 plus R2, which is 10 plus 20, which is 30 ohm. The total voltage V is 30 volt supplied by the battery, and hence the current I in the main circuit can be found out using Ohm's law as I equals V by R, which is equal to 1 ampere. So here we have the current 1 ampere. Next, sketch a graph of voltage versus time and the voltage across the 10 ohm for the voltage across the 10 ohm resistor. So part B, ideally speaking, if it were a circuit where the capacitor were not present, the graph would be a linear graph with a positive slope since the resistor obeys Ohm's law. But here, since we have a capacitor introduced and the capacitor slowly charges up to the voltage of the battery provided, which is 30 volt, the voltage will exponentially keep on decreasing, and hence the graph of voltage versus time, V versus T, is an exponential decay graph as such. Moving on to part C, determine the current through the 15 ohm resistor immediately after the switch is moved to position B. Now, when the switch is moved to position B, after a long period of time, remember, the 50 microfarad capacitor here, the 50 microfarad capacitor acts as a secondary voltage source, providing 30 volt of potential. It is then connected to a 15 ohm resistor and a 20 microfarad capacitor. Here is the equivalent circuit. Now, the capacitor on the left, which is 50 microfarad, starts to discharge, whereas the capacitor on the right, which is 20 microfarad, starts to slowly charge by using the potential that is provided by the 50 microfarad capacitor. Now, the two capacitors will start to discharge and charge one another up until the potential across both the capacitors matches. Now, to figure this out, let us first find out the total charge that is contained within the 50 microfarad capacitor. We know that capacitance C is defined as a ratio of charge to voltage, which means charge Q is capacitance times the voltage, which is 50 microfarad into 30 volt, giving me the combined total charge for just the 50 microfarad capacitor as 1500 microcoulomb. Now, as explained before, the voltage across this V1 should be equal to voltage across this V2, and the two capacitors will charge and discharge, or current will be allowed to flow in the circuit up until that particular point. Now, before we solve further, let's first start understanding how to solve part C of the question. Part C asks us to determine the current through the 15 ohm resistor immediately after the switch is moved to position B. Immediately after the switch is moved to position B, as we've done before for the first circuit. The 20 microfarad starts to charge and hence acts as a closed circuit. So the current I can be found out as current I is equal to V by R. The voltage provided is 30 volt, whereas the only resistance offered is by the 15 ohm resistor, and its resistance is 15 ohms. This equals to a current of 2 amperes. Hence the current I flowing here, let's call it I2. Let's call this I1 to avoid confusion. So this I2 is equal to 2 amperes. Moving on, let's answer part D of the question. Part D is an explanation partly provided already. They have asked us to determine the amount of charge stored in the upper plate of the 20 microfarad capacitor after a long time. We have explained this before. The two capacitors will charge and discharge up until the voltages are equal. Since voltage V is equal to Q by C, let us assume that the second capacitor, charges up to a charge of Q, let's say. Now, V is equal to Q by C. So if the second capacitor is charged up to a value of Q, then the first one loses exactly that many charges. So the charges left in the first capacitor is 1500 minus Q, where Q amount of charges are transferred onto the second capacitor of 20 microfarad, divided by its voltage. Now, we know that the voltages are going to be equal, so it doesn't matter what value we take. We'll take this as equal to V. Let me redo this. Yeah, we'll take this as V1, this as V2. Now, V is equal to Q by C, as stated before in this equation. The capacitance of the first one is 50 microfarad. This is equal to the voltage across the second capacitor, that is a 20 microfarad one, which has total of Q charges, which it stole from the first capacitor or took, divided by its capacitance, 20 microfarad. So the values cancel here as such, and you can simplify it further. Simplified, the value of Q is exactly 429 microcoulomb. So this is the amount of charge stored.